Hello, my name is Erin Carney, and I'm a senior at UMass Amherst, studying mechanical engineering and applied mathematics. I've been doing research on hafnium oxide layer-by-layer resistive switching devices with the Nanoscale Interface Transport and Energy Lab. So I've been making devices that could work for resistive random access memory, which is an alternative to flash memory. It is non-volatile, which means that it'll retain its memory state even if the device loses power. It is scalable, which means that for the different fabrication methods, it can be increased much easier than other devices. And it is versatile, so that it can be rewritten and read many times. It is a simple two-terminal structure, and it has the potential for analog electronics, neuromorphics, and multi-state memory applications. The goals of the research is to create devices with low read voltages, less than 1 volt, and to reduce the resistive switching speed to less than 10 nanoseconds and improve computing speeds. The other goal is to improve state retention to up to 10 years at 85 degrees Celsius. So resistive switching, and at least one method of it, occurs as alternating biases, electrical biases are sent through the device, and in this case, conductive filaments are constructed and deconstructed within the device. These are known as the high resistive states and the low resistive states. So for a more in-depth explanation, as a voltage is sent through the device, the oxygen vacancies, at least in my samples, are attracted to the negative electrode, which forms a conductive filament from the positive electrode to the negative electrode. As the bias is switched and reversed, the filament is deconstructed in a small space between the electrode and the rest of the filament. And as this is swapped, you can read and find the high resistive state and the low resistive state. So this research has been done before, and it is based on a paper that we read. They used different nanocrystals than hafnium oxide, but as you can see in the graphic, the idea is to use the ligands in the dendrimer to act as an adhesive for the nanocrystals to create an alternating structure that should hold everything together. To create this, we did an RCA clean on the substrate and washed it with deionized water, then submerged it in a dendrimer solution, washed with ethanol, and then dried with a nitrogen gas. We then dipped it in the nanocrystal solution. In my research's case, it's hafnium oxide. Then we washed it and dried it. So we repeat the dipping and submersion process multiple times to get the alternating layers, and then electrodes are deposited on the top. So one of our dipping methods was to dip half of it and expose half of the bottom electrode. This process was not completely successful because, as the topography results shown here show, the non-submerged side did not have a significant height difference than the submerged side. But we were able to do some conductive testing. It just wasn't very conclusive. So the potential issues with the research we've done is that the conductive AFM testing was not conclusive, which means that the platinum deposition may not be completely consistent, and there may be inconsistencies all over the substrate. We are also a year into the study, so we are questioning the stability of the ligands in the dendrimer solution and the nanocrystal solution. Other research in the lab has been going on about fabricating nanoribbons with the hafnium oxide solution. So this is the hafnium oxide and the oleic acid with no dendrimers. So it does show resistive switching behavior, which leads us to question the dendrimers more than the nanocrystal solution. So our conclusions are pointing towards that the extra length of the dendrimers are blocking the charge transport and are pushing us in our future research towards new fabrication methods other than the layer by layer dendrimer assembly, like the flow coated slowly into films or multi-layer structures. Thank you very much for listening, and I can't wait for your feedback.